we discuss with you field theory. In field theory, first topic, first unit is algebraic field extensions. Last lectures, we have studied the theorems of algebraic extensions, and now today we have discussed the algebraic extensions. What is the definition of algebraic extensions? Definition, now see here. Let E be an extension of F. An element alpha belongs to E is said to be algebraic over F if alpha is the root of non-constant polynomial p of x belongs to f of x, or an element alpha belongs to E is algebraic over F if there exists a non-constant polynomial p of x belongs to f of x such that p of alpha is equal to 0. P of alpha is equal to 0. Next one, a few remarks. If alpha belongs to E is not algebraic, then it is called transcendental over F. Transcendental over F. For any field F, second remark, every element alpha belongs to F is algebraic over F since there exists a non-zero polynomial p of x is equal to x minus alpha in f of x such that p of alpha is equal to 0. Example for algebraic extensions. An element root 3 belongs to R. R is a set field of real numbers, is algebraic over Q. Q is a field of rational numbers because there exists a non-constant polynomial p of x is equal to x square minus 3 belongs to q of x such that p of root 3 is equal to 0. Another example, one more example, the complex number I is equal to root of minus 1 is algebraic over Q since there exists a non-constant polynomial x square plus 1 belongs to Q of x such that I is the root of x square plus 1. One more theorem. If F is a subset of E with the fields and let U belongs to small u belongs to E be algebraic over F. Let P of x belongs to F be a polynomial of least degree such that P of u is equal to 0. Then prove that P of x is irreducible over F. Second, prove that if g of x belongs to f of x, capital F of x, it's so that g of u is equal to 0, then prove that p of x divides g of x. And one more bit, there is exactly one monic polynomial p of x belongs to f of x of least degree such that p of u is equal to 0. For prove this theorem, we consider contrary. For contrary, suppose that p of x belongs to f of x is a reducible polynomial. But reducible polynomial can be expressed as a product of two non-constant polynomials. Suppose that p1 of x, p2 of x belongs to f of x, such that p of x is equal to p1 of x multiply p2 of x. This implies that degree of p1 of x less than degree of p of x and degree of p2 of x less than degree of p2p of x. Then p of u is equal to 0 implies that p1 of u is equal to into p2 of u is equal to 0. This implies that p1 of u is equal to 0 or p2 of u is equal to 0. U satisfies a polynomial of degree less than degree of p of x, which is contradiction. The fact that p of x belongs to f of x be a polynomial of least degree such that p of u is equal to 0. Therefore, p of x is an irreducible polynomial over f. Now one more bit what is bit? If g of x belongs to f of x is such that g of u is equal to 0, then prove that p of x divides g of x. For prove this theorem, prove this bit, suppose that g of x belongs to f of x such that g of u is equal to 0. By division algorithm, g of x can be expressed as p of x into q of x plus r of x for some q of x, r of x belongs to capital F of x, where r of x is equal to 0 or degree of r of x less than degree of p of x. Since 0 is equal to g of u, that is implies that p of u multiply g of u plus r of u. But it is given that p of u is equal to 0. Therefore 0 into q of u plus r of u. Therefore r of u is equal to 0. But p of x belongs to f of x be a polynomial of least degree such that p of u is equal to 0. There does not exist r of x belongs to f of x such that degree of r of x less than degree of p of x and r of u is equal to 0. Therefore r of x is equal to 0. Therefore g of x is equal to p of x into q of x. Therefore p of x divides g of x. This is complete the proof. Third one proof, there is exactly one monic polynomial p of x belongs to f of x of least degree such that p of u is equal to 0. For proving this theorem, proving this bit, suppose that g of x belongs to f of x be a monic polynomial of least degree such that g of u is equal to 0. Then first one, p of x is not irreducible, therefore g of x is irreducible polynomial over f. And by second, p of x divides g of x, therefore p of x divides g of x, and here g of x divides p of x, here p of x divides g of x, and g of x divides p of x, therefore g of x is equal to p of x. Hence there is exactly one monic polynomial p of x belongs to f of x of least degree such that p of u is equal to 0. There is a theorem, let f is a subset of E with the fields and u belongs to E. Let f is a subset of E with the fields and u belongs to E be algebraic over f. Then prove that there exists a unique monic irreducible polynomial p of x belongs to f of x such that P of u is equal to 0. For proving this theorem, consider the set I is equal to f of x belongs to P of capital F of x such that f of u is equal to 0. Then I is an ideal of the ring capital F of x. Since for f of x belongs to I, g of x belongs to capital F of x, therefore f of u into g of u is equal to 0. Therefore f of x into g of x is equal to I. Now f of x is a principal ideal domain, therefore I is a principal ideal. There exists p of x belongs to I such that I is equal to generator of p of x is equal to p of x into g of x such that g of x belongs to f of x. We assume that p of x is a monic polynomial in f of x. Since if p of x is not monic, that is p of x is equal to a naught plus a1x plus dot 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 plus an x raised to n, with an is not equal to 0, and let g of x is equal to a0 inverse a0 plus an inverse a1x plus dot 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 plus an inverse an x raised to n. Then p of x is equal to a and g of x. This shows that p of x and g of x are associated in f of x. Hence, generator of p of x is equal to generator of g of x. Therefore, generator of p of x is equal to I is equal to set notations f of x belongs to capital F of x such that f of u is equal to 0. Since u belongs to E, capital E is algebraic over F, there exists a non-constant polynomial f of x belongs to capital F of x such that f of u is equal to 0. This implies that f of x belongs to I is equal to generator of p of x. F of x is equal to p of x into g of x for some g of x belongs to f of x. Therefore, p of x is a non-constant polynomial with degree of p of x less equal degree of f of x for all f of x belongs to I and f of x is not equal to 0. Call equation number 1. Therefore, p of x is an irreducible polynomial. If p of x is reducible, then p of x is equal to g of x into h of x. For some non-constant polynomials, g of x, h of x belongs to capital F of x. This implies that p of u is equal to 0, that is g of u into h of u is equal to 0. This implies that g of u is equal to 0 or h of u is equal to 0. This implies that g of x belongs to I or h of x belongs to I. But since degree of p of x is equal to degree of g of x plus degree of h of x, therefore degree of g of x greater than 0, degree of h of x greater than 0, therefore degree of g of x less than degree of p of x and degree of h of x less than degree of p of x, which is contradiction to first. Then there exists a monic irreducible polynomial p of x belongs to f of x such that p of u is equal to 0. Uniqueness. Suppose that p of x is equal to a naught plus a1x plus dot 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 plus x raised to n, and q of x is equal to b naught plus b1x plus dot 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 plus x raised to m. Be two irreducible monic polynomial in f of x such that p of u is equal to q of u is equal to 0. Then q of x belongs to I is equal to generator of p of x. This implies that q of x is equal to p of x into g of x for some g of x belongs to f of x. But q of x is a irreducible polynomial, therefore g of x is a unit. That is for g of x belongs to capital F. And hence degree of q of x is equal to degree of p of x is equal to n. That is m is equal to n. Now p of u minus g of u is equal to 0. P of x minus g of x belongs to I. P of x minus g of x is equal to 0. Therefore p of x is equal to g of x. This is uniqueness is proved. This is uniqueness is